Good afternoon, everyone. First, I would like to thank the organizing committee for inviting me here. And so I'm Suvasthika Indrajith. I'm a postdoc researcher at the Institut Lumière, Matière in Lyon, France. And today I would like to talk about a recent paper that we have published on near-infrared absorption and radiative cooling of pH dimer in electrostatic ion beam storage ring. You hear me well? Thank you. So here's the outline of my talk. I will first present the context and motivation behind our study, and then I would like to present some the experimental different experimental setup that we use here, and also the notion of behind radiative cooling, and also present what's the particular study we have here. And then I move on to experimental and theoretical results and a quick summary. So in the interstellar medium, more than 300 molecules have been identified as large, complex carbonized molecules. Moreover, they are polycyclic aromatic hydrocarbons, which are called PAHs, are also expected to be present. They have also proposed as possible carriers of the unidentified infrared band emissions in the 80s, and are since then believed to be distributed ubiquitously in the whole interstellar medium. This leads to a selection of species that can survive, mostly assuming that there are large pHs containing more than 50 carbon atoms. Ionized dimers, on the other hand, dimers of PAHs are also being shown to be very effective candidates to carry the extended red emission in this photodissociation region. Since they have large heat capacity and very low ionizing energies than the isolated pH molecules, for example, they are predicted to be more stable. This could make them very attractive candidates to survive in specific astrophysical environments, those being very dilute environments, 10 to the minus 14 millibar, very scarce interaction rates, having very scarce interaction rates, and being at very low temperature. This leads to the B1 subject to various types of radiation, including UV photons, for example. And numerous experimental and also theoretical studies have been carried out with the aim to unravel how they are formed, how they survive in such harsh environments. In order to understand this, one of the key is to look at the cooling dynamics of these pHs to understand their stability and therefore to also estimate the evolution in the space. So to explain briefly the concept of radiative cooling, what we aim here is to follow the ultra-slow molecular relaxation processes such as fragmentation, infrared emissions, and so on that competes in new time domain in order to understand their molecular formation and how they survive in the affecting their abundance. So coming back to it, the processes, when an ion is electronically excited via UV, after absorption of UV photons, several fast internal conversion processes can occur, bringing back the molecule to its electronically excited states with high vibrational energy. This this internally hot molecule might either dissociate by losing hydrogen, or mainly in case of the pH is losing C2H2 path, or survive by cooling through infrared emissions. This process being very slow process, taking up to seconds. Sometimes under highly isolated conditions, isolated astrophysical conditions, other energy conversion process may occur, which is called here, which is called inverse internal conversion. So this, what happened is that it's bringing the molecule back to its electronically excited state and cools down very fast, very efficient. It's an efficient process, bringing the molecule back, rapidly reduce the internal energy, which saves them from other destruction processes. This process is called recurrent fluorescence, also called Poincaré fluorescence. This latter process has been already observed for a lot of pH monomers, such as naphthalene, anthracene, the tetracene, and also more recently cyanonaphthalene, which have also been detected in those molecular clouds, for example. So one way to monitor this cooling process is to use electrostatic ion beam storage ring to clearly monitor the dynamics of initially hot ions upon cooling. Compared to magnetic device, here there will be no magnetic field mixings, meaning that it's more compact than a magnetic confinement ring, so it's kind of cheaper, I guess. And also there's only it's cut, but there's only electrostatic field, so there's no mass limitation. It's mass over charge independent for the given applied voltage. So around the world there are there exist several electrostatic ion beam storage rings with their own, of course, uniqueness. Some of them are also cryogenic here, and I will come back to that. What we have used in our specific case is mini ring. It's a storage ring which is located at Institut Lumière Matière, where I am a postdoc. It's a very small size tabletop apparatus operating at room temperature, and it has a higher background gas pressure. One of the advantages of mini ring is that it has a higher sampling rate, where we can store ions for short storage time, up to 500 milliseconds. On the other hand, we have also used a DESIRE, which stands for a double electrostatic ion ring experiment. This is an electrostatic storage ring located in Stockholm University in Sweden. You will have a much more clear, maybe, presentation of DESIRE, my former colleague José, just right after me. So DESIRE is much bigger than a mini ring, obviously, and it's unique because of its cryogenic chamber, which is cooled at 13 Kelvin. Also because it's double ring here. It operates at ultra high vacuum at 10 to the minus 14 millibar. Now you can maybe understand how it's very much useful to mimic the astrophysical condition that I've just told you earlier in the context. And has two different energy platforms where we can produce our ions, cationic and anionic also. And it helps all these conditions helps to have to store a very long lifetime of our ions, up to even hours. So in the present study, our aim is to investigate the radiative cooling of naphthalene dimer cations, which are represented here, by recording the evolution of the action spectra with time. And cationic dimers exhibit several absorption features, which is illustrated here. The charge resonance CR patterns stem from the interaction between resonance or equivalent configurations, this naphthalene and naphthalene neutral, naphthalene plus, and naphthalene plus, naphthalene neutral, coupled with the charge transfer interaction resulting into energy splitting here, this delta zero, at equilibrium geometry. Together with the global energy lowering due to polarization and dispersion interaction, such resonant patterns can also exist with the dimer states correlation with monomer cations excited state, which is called also local excited state. So coming to the experimental results, quickly, just again, I will present. This is the quick overview of those both experimental setups. So in Miniring, both we produce our ions, our cation dimer cations, through an ECR source. So it's just a plasma where we can produce our cations, and then they are selected by a bending magnet and then just go through this ion ring. In the case of Desiree, we have, of course, just used one of the rings. And then in those two setups, it's also possible to use laser. Laser beam here is crossed over 90 degrees, the straight section, to probe the in rotational temperatures and also the population in different states. We then detect our cationic fragments. In the case of Desiree, we detect them through a fragment detector here, which is deflected. The ions are deflected, and also the neutral ones through these imaging detectors. So this would be a typical raw experimental data, where we show the counts of the neutral fragments as a function fragment detected as a function of storage time. Here I only show you I cut it from 0 to 1 only. The first milliseconds are attributed to the spontaneous dissociation of internally hot naphthalene dimers upon cooling. With the sharp, then we see sharp peaks here, which corresponds to the laser-induced dissociation. And if we just look at one sharp peak here, we can clearly see this difference between the charged fragment here in blue coming before the neutral fragment comes. So there are two different detectors coming to at two different detectors, and these are of course integrated over a wavelength range. Here I present a 2D map of the action spectra that we have of the laser-induced naphthalene dimer dissociation. The charge fragment counts as a function of photon energy and the storage time here. The red line is the exponential fit, actually, of this CR charge resonant band position determined at the maximum intensity. So here, I will come back a bit later also of what's here, but what you see here is this maximum band here, and it's that's what this line is represented over this as a function of storage time. And this CR band was found to become narrower and to shift towards higher energy as a function of storage time, as you can see here. Here, okay, on the top bottom panel, you have this summed over 0 to 5 seconds. So it's basically representing this part here, which is very close to lower energy, so lower than 1 eV. And then when we look a bit further on the summed over 20 to 30 seconds here, you can see this narrowing and also the shift. So in order to determine an experimental characteristic shift time, this CR band position has been plotted as a function of storage time. And we then use this double exponential fit to characterize the time evolution of the CR band position. We attribute the shift and the narrowing of the CR band with the time of the radiative cooling here. Unlike other pH monomer cations that we've already been studied, this dimer cations actually only goes through low-lying since it does not have low-lying excitation, electronic excitation to mediate any recurrent fluorescence that can happen. There is only to prevent the dissociation process. It cools down only via vibrational emissions in the infrared region. So we then compared the spectra recorded at Desiree here This is what I represent in blue, okay? Summed over, as I said, is 0 to 5 seconds, and then 20 to 30 seconds, so very at the beginning and then at the end of the storage time. And what we call, we compare this, of course, with the mirroring data that we have taken. And when we, we have this mirroring hot condition and mirroring cold condition. What I mean here is that, once again, Desiree is cooled down, so it's very cryogenic, it's very cold, compared to mirroring, which is operated at room temperature. So in order to really compare and see if there's overlap or anything, what we did is we changed the source condition of the mirroring. Both of them the ions are produced via ECR source, but in the mirroring we can tune in the source in order to produce like cold plasma by increasing a lot of the pressure that we inject. So by this we can actually see a very good overlap, and also again this narrowing and this shift, blue shift with decreasing temperature. As I said, we start with the hot condition and then we cool down. So we are decreasing in temperature. That's why we see over the storage time we see a blue shift. And this charge resonance band blue shift can be considered as a marker of the radiative infrared cooling. So now, of course, any experimental studies and results need support from the theoretical simulation. So we have collaborated with our colleagues in Toulouse, with Matière and Fernand Spiegelman. They are the one who did all this calculations, simulations, and so on. So they first determined the electronic structure of this naphthalene dimer cations using this so-called DFTB XI calculation, so density functional base type binding, with this local excitation and configuration interaction. So they added this part to be able to really take into account this resonance between these two molecules. And this has already they have already used this for other PAH molecules, also pyrene, and it's also worked. This provides this potential energy surface with the dimer, displaying an overall agreement with this CASPT2 simulation that's also been taken as a reference. And you can see it's a very good agreement. So for this geometry. So with these corrected energy potential energy curves, the lowest energy geometry remains as the twisted parallel twisted configuration. This is being the most stable geometry at here, with a dissociation energy of 1.4 eV. One can observe that in the twisted form, the LEX states splitting is much smaller compared to the one for the parallel superimposed. And also here we can see the degeneration, whereas here there's no splitting. Next is of course, to use this corrected DFTB XI scheme for electronic structure calculation. We simulated the absorption spectra using this parallel tempering Monte Carlo scheme for a temperature range from 10 to 500. So they started with the low temperature and then just increased the temperature and looked at the different bands that they were having. So the colors are the one for the dimer, and you can see this. They also added the monomer, the bands for the monomer. And when we look at the charge transfer, as we increase the temperature, this CR band redshift, and it's also broadening compared to the LE band here, which it stays here and it's also broadening. And then when we look at they also look at the vertical band position, and they see that it's actually corresponding to just the configuration, the isomerization of both of the dimers. Here presented just a snapshot that they taken from 300 of these molecules. Yeah, and then so when they just took the maximum peak position here, and and when we look at the function of temperature, we can quickly we can see that it's actually corresponding to a linear fit, linear regression, and with this we can have this temperature, this canonical temperature. Then what they did. So this time it's some other colleagues from Toulouse. There's Christine Joblin and Dominique Toublanc. They looked at. They wanted to look at the modeling of infrared cooling using Monte Carlo also. So what they did is the cooling curve of this naphthalene dimer cations have been simulated using this kinetic Monte Carlo model, where they taken into account this already known infrared cooling rate. I'm really not an experimentalist, I want to say that, so the theoretical part is really not my expertise, so I really try to tell my best about these results. But just briefly what they do, they have this internal energy as a function of time, and then from this they get to the microcanonical temperature, and from that they just try to simulate the CR band position that we already saw from the, and compare this with the experimental data, which is here dotted. And what they see that it's a very good agreement between the model result and the experimental data, and obtained with the value of decoupling energy, which is between 650 and 0. Okay, so now to sum up, so since what we have seen is this between these two charge resonance band position. What we saw with the experimentally is that we have a blue shift of this band as a function of storage time, and this could be seen as a marker and as to monitor the cooling rate, the infrared cooling rate. And in contrast to other PAH monomers here, naphthalene dimer cations has slower cooling rates, and mostly it's only through vibrational, infrared vibrational emission. There's no recurrent fluorescence. When we looked at the absorption spectrum from this 0 to 2.5 EV and compared the CR bands and the LE bands together with the experimental and this Monte Carlo model, what we see is a redshift on the broadening of the CR band with increasing temperature. And then lastly, so since large size ionized molecular clusters often have a dimer or a trimer core, this present study is a step towards a better understanding of the elementary process in pH cluster formations via excited states. So such processes are need to be considered when we want to understand or evaluate the survival of these species in those very harsh environments. With this, I would like to thank all the collaborators and my supervisor, Jérôme Bernard, who really did the experiment with Serge also in Miniring, and also collaborated with all the other theoreticians and the people from Désiré team. And yeah, thank you for your attention.
Thank you very much. Now the floor is open for questions. Otherwise, I can ask to break the ice while you think your questions. What's your next step? Like, what's your next PAH that you would like to study?
Oh, that's a good question. Right now, what we looked at they also done some already done some experiments in dimer of anthracene, if I'm correct, but those are not yet published. But we also looking at the isomerization of both two pH. Yeah, the isomer effect of two pH isomers. So this azulene and naphthalene, they have really the same. They are isomers. So wanted to see if when we cool down, we can really look at the isomerization. And again, this is being done in Meniering, and with the same source condition also. So it's really, yeah.
Very nice. So any other questions from the audience? Okay, then let's thank the speaker again.